In this lecture video, we're going to learn how to test a claim about a population proportion. We'll start by listing out the steps of hypothesis testing. Step 1 is to determine the null and alternative hypotheses. Step 2 is to calculate the test statistic. Step 3 is to find the p-value or critical value, depending on which method you choose. And step 4 is to determine and state the conclusion. It's also important that we're using the correct notation. Lowercase n is the sample size, or sometimes the number of trials. Lowercase p is the population proportion. Lowercase q is 1 minus p. And p hat is the sample proportion. The test statistic for testing a claim about a proportion is found using this equation. Z is equal to p hat minus p, the difference between the sample proportion and the population proportion, divided by the square root of the product of p and q over n. Notice that our test statistic in this case is a z, so you can use your z-table. I will also show you how to use your calculator. The function that we'll need for this is 1-prop z-test. In this first example, we are told that in a survey of 1,500 households randomly selected, it is found that 47% of them have a high-definition television. We are going to use a 0.01 significance level to test the claim that fewer than half of all households have a high-definition television. Let's start by identifying the claim. The claim is that fewer than half of all households have a high-definition TV. Symbolically, we can write this as p is less than 0.5. We use p since we're discussing a proportion, and we write less than 0.5 because the claim is fewer than half. Let's also list out the information that we're given. We have some sample data. The sample size is 1,500, and the sample proportion that was found is 0.47, so that's our p hat. Also notice that we are asked to use a 0.01 significance level, so that's our value for alpha. Now we're ready to list our null and alternative hypotheses. The null hypothesis, H0, must be a statement of equality. So we can write that the population proportion is equal to 0.5. That is, it's not so different from half. For the alternative hypothesis, H1, we will represent the claim. We'll write that the population proportion is less than 0.5. This alternative hypothesis lets us know that this will be a left-tailed test. If this was a greater than statement, it would be a right-tailed test, and if it was a not equals to statement, it would be a two-tailed test. Let's start our picture. We have our left-tailed test with alpha equal to 0.01. And since we're working with a proportion, our horizontal axis is values for z. Now we're ready to calculate the test statistic. By hand, we calculate the test statistic z by finding p hat minus p divided by the square root of p times q over n. In this example, p hat is 0.47, and for the population proportion, we use the value found in the null and alternative hypotheses, 0.5. Remember, we're assuming that the null hypothesis is true until proven otherwise. And since p is equal to 0.5, q is also equal to 0.5, 1 minus p. And n, the sample size, is 1,500. Putting this into our calculators and rounding to 2 decimal places, we find a test statistic of z equal to negative 2.32. Next, we find either the critical value or the p-value. I'll show you both options here. Remember that the critical value is the score that cuts off the tail corresponding to alpha. So in order to find our critical value, we need to find a z-score that has a left area of 0.01. You can use your z-table and look in the body of the table to find the area closest to 0.01, or you can use the INV norm function in your calculator. Either way, we find the critical value is equal to negative 2.33. Now that we know what this critical value is, notice that we can place our test statistic on the graph. The test statistic is negative 2.32, which is not quite as extreme as negative 2.33. So by comparing the critical value with the test statistic, we can see that we are not in the critical region and we will not reject the null. We could have instead calculated the p-value. Remember, these methods are equivalent. The p-value is the area to the left of the test statistic. With a test statistic of negative 2.32, we can again use our z-table or our calculators to find the area to the left of this test statistic. Either way, you should find a p-value of 0.0102. Compare this p-value to alpha. It is just barely larger than alpha. And since the area to the left of the test statistic is larger than alpha, that also tells us that we are not in the rejection region. We failed to reject the null. Let's determine and state this conclusion clearly. Since our p-value was greater than alpha, that is 0.0102 is greater than 0.01, we failed to reject the null. Remember that the null is assumed to be true until proven otherwise, and our value was not extreme enough to cause us to reject it. To state this conclusion as a full sentence, we would write something like this. There is not sufficient evidence to reject the null. In other words, there is insufficient evidence to support the claim that fewer than half of all households have an HD TV. It's important that we state our conclusion clearly using full sentences once we've conducted the hypothesis test. Let's go on to our next example, and this time we'll use our calculators. In this example, we are told that in a research poll, 1,002 adults were asked if they felt vulnerable to identity theft. 531 of them said yes. Use a 0.05 significance level to test a claim that the majority of adults feel vulnerable to identity theft. Let's start by stating the claim. For this example, the claim is that the majority of adults feel vulnerable to identity theft. To write this symbolically, we would write that the population proportion is greater than 0.5. A majority is anything greater than half, and in terms of proportions, that would be greater than 0.5. The sample data that we have is this. The sample size is equal to 1,002, and our sample proportion is equal to 531 divided by 1,002, or 0.52994. Now we're ready to state the null hypothesis. The null hypothesis always needs to be a statement of equality, so we'll take the value from our claim and write that the population proportion is equal to 0.5. For the alternative hypothesis, we'll represent the claim. We'll write that the population proportion is greater than 0.5. Now we can calculate the test statistic. Working by hand, we have our sample proportion, 0.52994, minus the population proportion, 0.5, found in the null hypothesis, divided by the square root of p, 0.5, times q, 1 minus p, or also 0.5, divided by n, 1,002. This gives us a z-score of 1.90. Since the alternative hypothesis has a greater than symbol in it, this is a right-tailed test, with our alpha equal to 0.05. For step 3, we calculate either the p-value or the critical value. Once you find which method you prefer, you should stick with that, but I'll show them both to you here again. Since we have a right-tailed test, the p-value is the area to the right of our test statistic that we just found in step 2. If you take a look at your z-table, you'll find that a z-score of 1.90 has a left area of 0.9713. That means that it has a right area of 1 minus 0.9713. We have a right area of 0.0287. That's our p-value. And using this p-value method, we can determine the conclusion. We compare the p-value to alpha. This time we found that the p-value is 0.0287, and we know that alpha is 0.05. So the p-value is smaller than alpha. With a p-value less than alpha, we move to reject the null. Now let's back up to step 3 and go the critical value route. Instead of calculating the p-value, we would find the critical value that's associated with alpha. Our critical value has a right area of 0.05, which means that it has a left area of 0.95. Looking at your z-table, you'll find that the critical value is equal to 1.645. Now compare that to our test statistic. The test statistic is 1.9, which is more extreme than the critical value. That puts the test statistic in the rejection region, and we again reject the null. Comparing the test statistic and the critical value, we have that 1.90 is more extreme in the right tail than 1.645. We have the same conclusion to reject the null. With rejecting the null, that means that we have sufficient evidence then to support the claim. So we might say something like this: there is sufficient evidence to support the claim that the majority of adults feel vulnerable to identity theft. Let's try out the same example again with our calculator. We want to use the one-prop z-test. We can find that in the Stat menu by toggling over to Tests. One-prop z-test is option 5. P0 refers to the proportion that's present in the null hypothesis. In this case, that's 0.5. We also will enter our x and n value. N is the sample size, 1002, and x represents the number of successes. And in this case, that would be the 531 that said yes. We have a right-tailed test. That is, the alternative hypothesis is that the population proportion is greater than the value found in the null hypothesis. And finally, we can press enter on calculate. Notice that we first have that the alternative hypothesis is that the proportion is greater than 0.5. Next, we're given the test statistic, z equal to 1.90. Following that, we have the p-value of 0.0290. We have our sample proportion and our sample size. Using our calculators, we found a slightly different p-value of 0.0290. This is due to the rounding that we did as part of calculating the test statistic. However, either of these two p-values would lead us to the same conclusion. Let's take a look at one last example. Here we have that voting records show that 61% of eligible voters actually did vote in a recent presidential election. In a survey of 1,002 people, 70% say they voted in that election. We're going to use these survey results and a 0.01 significance level to test the claim that the percentage of all voters who say that they voted is equal to 61%. As always, let's start by stating the claim. The claim is that the percentage of all voters who say that they voted is equal to 61%. To write this symbolically, we have a proportion, p, equal to 0.61. We are also told to use a significance level of 0.01, so that's our value for alpha. Since the claim is a statement of equality, we already know that this will be a two-tailed test, and that alpha will be split in half into the two tails. Each tail will have an area of 0.005. Now let's consider the null hypothesis. The null hypothesis is a statement of equality, and so is our claim. So in this instance, the null hypothesis will match up with our claim. That also means that the alternative hypothesis will be a statement of not equals. The proportion is not equal to 0.61. The next step is to calculate the test statistic. And let's practice doing that with our calculators. We would like the one-prop z-test, which we can find by pressing Stat, then toggling over to Tests and selecting the fifth option. To use the one-prop z-test, we need the population proportion that's found in the null hypothesis. In this case, that's 0.61. We also need the x and n value. N is the sample size, which in this case is 1,002. But we are told that 70% said that they voted. We don't have the actual number of people. We're going to need to calculate that first. 70% of 1,002 people is 701.4. We can't have partial people, so we'll round this to 701 and take that back to our one-prop z-test. Now we have 701 for our x value. This is also a two-tailed test, so we need to select the not equals to option. And finally, we'll press enter when calculate is highlighted. Now we have our test statistic of 5.81, rounded to 2 decimal places. We are also given our p-value, 6.083 times 10 to the negative 9th. Also notice one more thing. Since we use 701 for our x value, we have a sample proportion here of 0.6996. It's not exactly 70% like we were given in the problem, but it's very close. Let's take this information back to the example. We found our test statistic of 5.81. We were also given the p-value of 6.08 times 10 to the negative 9th. If we were to write this in standard form, we would need 8 zeros before the 608. In other words, rounding to 4 decimal places, this would be equal to 0. One quick side note, just in case you're doing this by hand. If you were to calculate the test statistic by hand, you could use 0.70 exactly for the sample proportion, which would give you a test statistic instead of 5.84. Close, but not exactly the same. In this situation, calculating it by hand may actually be more accurate because we're using the information given in the example and not having to round our x value. And if you take this value for z and look at your z table, scrolling down to the very bottom of the table, we max out at a z-score of 3.49. We don't have 5.81 or 5.84. Any z-score above 3.5 is going to have a left area greater than 0.9999, which means that it has a right area less than 0.0001. Rounding to 4 decimal places, this gives us a left area of 1 and a right area of 0. Our final step is to determine and state the conclusion. Clearly, our p-value here is smaller than alpha, because rounding to 4 decimal places, it's 0, which is very much smaller than alpha. So our concluding statement would be to reject the null. But look closely. The null hypothesis was our claim. So in rejecting the null, we have effectively rejected the claim. So our concluding statement might read something like this. There is sufficient evidence to reject the claim that the percentage of voters who say that they voted is 61%. A quick note for those of you that prefer the critical value method, you can use the INV norm function in your calculator or your z-table to find the two critical values. The left critical value here has a left area of 0.005, and we find a z-score of negative 2.575. The right critical value over here has a left area of 0.995, which corresponds to a z-score of positive 2.575. Clearly, our test statistic is way farther to the right, so we would still move to reject the null based on the fact that the test statistic is more extreme than the critical value. And that concludes this lecture video on how to test a claim about a population proportion.